In the previous lecture, we talked about energy levels of different electrons when they're orbiting around in an atom. And there are higher energy levels when the electron has a wider orbit, and then when it's very close in, those are low energy orbits. The way that this is usually described, and we'll do that a lot in this course, is like a kind of a ladder energy diagram where higher energies are higher up on the graph. There's one energy level, the ith level, and then a lower energy level would be lower on the graph down here. And then, of course, there's always going to be some so-called ground state, the lowest energy level that an electron can possibly get into. And that would be the lowest one on the paper. You might usually put that at the bottom of your diagram, define that as the, well, you could define that as a zero energy. Anyway, the energy of the ground state. Now, how are we going to find out what these energy levels are? The best way is if an electron were to change its energy level. For example, if it were to go from a higher energy level to a lower energy level. Wait a minute. Is that possible? Don't we have to have conservation of energy here? Yes, we do. If an electron gives up energy, it's like going down a stair step. It's a quantized amount of energy, EI, that's E initial, minus EF, E final. That energy can't be destroyed. It can't just disappear from the universe. It has to go somewhere else. One possible way it could do that is if the atom was involved in a collision with another atom, or an electron or some other particle. The collision could carry away some energy, and the electron could drop down from a higher energy level to a low energy level. The way that I'm most interested in this course of how an electron, what happens when an electron gives up this amount of energy, is when it transfers the energy to the creation of a photon. Yes, a photon can actually be created. A little packet of energy gets created out of nothing when energy is liberated or released from an electron. In fact, that happens all the time. It's happening millions of times a second continually here. This is a very common process. So photons get produced with an energy which is the energy difference between these two levels. So there's the energy difference, and we know what the frequency of the photon has to be that got produced. It has to have exactly h times f, exactly that much energy corresponding to this energy difference of levels. That tells me only a specific frequency of photon. Therefore, only a specific wavelength of photon can be associated with, produced by, the electron dropping between these two levels. That means that even if we can't get inside the energy levels of an atom, we can infer what those energy levels are by solving the puzzle. Let's just look at the photons that come out of an atom, and there will be a series of discrete quantized photons having particular frequencies, and no other frequencies, only the frequencies corresponding to this energy level difference. And of course, all atoms will have electrons that have many different levels. And so anytime an electron changes between any of these two levels, depending on what the energy differences are, that is going to produce a photon of a particular frequency. If we can collect all of the different frequencies of photons coming out of this atom, we could piece together and reconstruct what all those energy levels were, because we know all of their energy differences. That's a fairly hard piece of work. If I make you do it, I'm only going to give you very, very simple atoms that maybe just have three levels. You know, a ground state, one upper, and then a higher upper level. By the way, when an electron is in the ground state, if it moves up to a higher level, that's called an excited energy level. That's the lingo, the terminology. And any process which bumps the electron up here, if it acquires some energy, that's called excitation. And of course, if it goes down, that's de-excitation. These are not human emotions and so on. I mean, I know this is pretty exciting stuff, but that's the technical term when an electron gets excited, when an atom gets excited. It has to absorb energy from somewhere. That's interesting. How's that going to happen? We still have to balance the books. We have to have energy conservation. Could a photon be involved in the process? Yes, the opposite process to what I've drawn here could happen. Instead of having a photon flying out of the atom being created from nothing, what happens if a photon came into the atom, was absorbed by the electron in the ground state, giving up its energy. If it had exactly this amount of energy, if it had exactly the right frequency corresponding to this energy difference, it could cause the electron, when it absorbs a photon, to jump up and be excited. So that happens too. Photons can be absorbed by sending electrons up the energy ladder. Photons can be emitted when the electrons drop back down the energy ladder. So I'm going to give you only really one example in this lecture of a real atom with real energy levels, which was painstakingly reconstructed by a lot of physicists working over years without knowing what the big picture was, but they gradually, empirically came to a big picture, and that was through the study of the simplest atom, which has only one electron orbiting around in it. That's hydrogen. So that's the simplest one to study. But a lot of the principles that we see in hydrogen actually apply to all other atoms too, even when there's more electrons going around. Usually, the energy level differences that you see are for the outermost electron of the atom. And of course, in the case of hydrogen, that's the only electron there is. So what do we see in the case of hydrogen? You see, when you heat up hydrogen, that means collisions will raise electrons to various excited energy level states. Then the electrons want to drop back down. And they drop back down by certain steps. And each step corresponds to a photon of a particular frequency or a particular wavelength. And the wavelengths, or the frequencies, that you get out of a hydrogen atom obey a very distinctive pattern. This is a clue about what the energy levels were, because every one of these photons is the energy difference between two levels in hydrogen, two electron energies. And so what you actually see is there's one here. They're all multiples of this magic number, 13.6 electron volts. Wonder why that is. That is the minimum amount of energy a photon needs to have, to completely liberate an electron to where it completely escapes from the atom. This would be like that work function that we talked about earlier in the photoelectric effect. See, these energy levels get closer and closer together as you get to high energy levels, but eventually there is a maximum energy level, and above that, what happens if more energy comes in? The electron cleanly escapes. It leaves the atom. It becomes an ion and a free electron. That's the process of ionization. Well, it turns out that this is the amount of energy it takes to completely ionize an electron, make it escape out of the ground state of hydrogen. That's a lot of energy. That corresponds to an ultraviolet photon. We don't have those photons around on the Earth in the air normally. The sun doesn't produce very many of those photons. They'd be quite harmful to have such a high energy photon. If it got absorbed in our molecules, it would mess them up and rearrange them. But fortunately, what few ones that the sun emits are pretty much blocked out by ozone and absorbed and other things, water vapor and so on. So they don't, oxygen, they just don't get down to the Earth to mess us up generally. But if you have a special experimental setup in a laboratory, you could produce these photons, and you would see that you have to have a minimum of this amount of energy to completely liberate an electron to where it escapes from the hydrogen atom. And this is a typical number for most other atoms too. So it turns out that producing ions, it requires ionizing radiation, and it's usually in the ultraviolet, or maybe the X-rays would certainly have enough energy to do it. And that's harmful radiation. We don't want to have a lot of that around. Well, all right, so the energies of these different hydrogen photons correspond to distinctive multiples of this ionization energy. In other words, for example, well, I'll give you an example on the next page. All right, actually, all of these, the pattern of the emission lines that are produced in a hydrogen atom, there's actually a more detailed lecture about this that I'm going to ask you to watch. I'm just going to give you the result right here. They can all be explained in a fairly simple way if the electron orbiting in a hydrogen atom has a series of quantum states, a series of orbits, which are described this way. if the energy of the electron is minus 13.6 electron volts divided by the orbital number n squared. So the energy is minus 13.6 electron volts over n squared. Now let's first check and see if this makes sense for very high orbits, high energy orbits, where the electron is very far away from the proton. Well, then n is getting very large. So n could be hundreds, n could be thousands. Well, in that case, what does the energy of the orbit go to? Minus 13.6 electron volts divided by thousands and so on. It's practically zero. So as n goes to infinity, what does this formula say is the electron energy? That's right. The electron energy goes to zero. Zero, the way I've described it here, zero is the energy of an electron as it's just escaping, as it's becoming free, as it's ionized. So going for, and what's the lowest energy level here that you could have in an electron? The ground state is n equals 1. It's a quantum number if you want to know, but anyway, the n equals 1 level is a minus 13.6 electron volts. Why a minus? Because energy was released. That's the potential energy is negative. You've got a plus charge and a minus charge held together. You have to do work on the system to separate them. But initially, there is negative potential energy. How much work would you have to do? What would the work function be to go from n equals 1 to basically n equals infinity? You'd be going from minus 13.6 electron volts all the way up to 0 electron volts. It would be ionized. So this formula makes perfectly good sense. It has the ionization energy, 13.6 electron volts of hydrogen, in the formula. The only thing which is not derived here is, well, why do the energy levels go as 1 over the quantum number squared? That can be explained. That was explained in Niels Bohr's model of the atom. It's not a perfectly accurate model of the electron orbiting around the proton, but it happens to give the correct numbers. It gives this formula which can correctly produce the entire spectrum of all emission lines, all absorption lines produced by hydrogen. Although you don't have to know the derivation of it, his idea was that electrons have quantized amounts of angular momentum, and they cannot have any other amounts of angular momentum in between. They come in quantum amounts as they orbit the proton, and if you make that assumption, that was a brilliant idea, very close to the truth, if you put that assumption in, then you derive basically, this is the Bohr formula for the energies of the electron levels. Now, if I want to know what the photon energies are, I just have to take the energy of the starting level minus the energy of the finishing level, and that energy difference is equal to HF. That energy difference here is equal to the energy of the photon that goes between those two energy levels. Anyway, I said this is not exactly perfect because Bohr's idealized model of an atom still is thinking of electrons as if they were going like planets in orbit around a positively charged center. But of course, as we discussed earlier, it's not really like that. Really, there's a cloud of probabilities that the electron just is there, like a standing wave. If you believe this sort of classical idea that an electron is like a planet orbiting around a proton, you would see in this case that it's accelerating all the time. Why is it accelerating? Because it would have like a velocity. It's not really true, it's not. Because it just is at all these places simultaneously. But if you assigned a velocity to it, then of course every time it goes around here, the velocity is changing its direction. A change in direction, that means an acceleration. And of course, if anything is accelerating, that it's going to radiate away its energy and lose energy. Because accelerating charges do lose energy. And so the electron, Bohr realized this was a problem. This was a hole in his theory. He realized the electron would very rapidly, in about a millionth of a second, it would spiral in down here, lose all of its energy, and collide with the proton, which of course never happens. We wouldn't have any atoms. We wouldn't be here if that were really true. Anyway, he also worked out, and we talked about this in the last lecture, the implied velocity. if this orbital picture were right, if the Bohr picture were literally correct, the implied velocity is very, very fast. It's like almost 1% the speed of light, much, 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 much faster than the speeds of molecules moving around in this room right now, which is thousands of times less. All right, so Bohr atom, a very insightful picture that has elements of the truth in it. It's much more realistic than anything that came before it, and it's very practical because it's going to allow us, well, that means you, to work out actual photon frequencies and wavelengths from atoms, hydrogen atoms. All right, so here is the energy level diagram. This is now, I'm trying to draw this actually to scale, for the electron in the hydrogen atom. So you talk about hydrogen in its ground state. That really just means that the electron is in its closest, smallest low energy orbit. Oh, look what we did here. We actually, in this diagram, depending on which one is more convenient, you might draw the ground state energy to be 0 electron volts. You better get comfortable with these. And the amount of energy it takes to completely escape is, oh, we already did this before, the ionization energy, 13.6 electron volts. So I'm now, what did I do? I took the previous formula, the previous Bohr formula, and I just added 13.6 electron volts to everything. I arbitrarily changed my energy level 0 point. That's okay to do that. But this, I'm still using the Bohr formula here pretty accurately. And so you see that the energy, there's n equals 2 up there. N equals 3, n equals 4. And you can see that because 1 over n squared, as n gets very, very large, that's going to 0. The spacing between, the 50th and the 51st level, and the 109th and the 110th level, actually I worked in that in radio astronomy, these spacings become very, very small. And so these energy levels of the very high energy orbits of the electron are just blending together into what's called a continuum of energies, and finally at this threshold of 13.6 electron volts above the ground state, the electron finds it's free. It has enough energy to take off and leave and be ionized. So now that we know these energy levels, we can work out the energy and the frequency of any photon produced by any transition. For example, let's look at all of the photons that would be produced when the final level is level 2. All right, let's suppose that photons are being emitted. So if they're being emitted, then the initial level has to be above level 2. They have to have had more energy to start with, and they gave up some of their energy when they went down to 10.2 electron volts. For example, level 3 to level 2, how much energy is that? The photon has picked up, what is that, 1.9 electron volts. From level, so that corresponds to a red photon. Fairly low frequency, you could see it. Level 4 to level 2, ooh, that one's picked up 2.6 electron volts. You can check the numbers. 2.6 electron volts, actually I think we checked these numbers in the previous lecture. That corresponds to approximately the wavelength of green, blue-green light. How about from level 5? Well, that's going to correspond to blue light. That's a bit more. It's like 3-something electron volts, and so on. So that was just keeping track of the energy level changes that ended you up on level 2. 3 to 2, 4 to 2, 5 to 2, and so on. How about energy levels that would drop you down to level 1, where level 1 is the final level? Those look like they're going to be bigger energies, right? For example, you could go from 2 to 1. That's a bunch of energy there. 10.2 electron volts. That is a photon with a frequency that puts it in the ultraviolet part of the spectrum. So this is an ultraviolet part. Now let's see. Level 3 down to level 1, that's even more energy, 12.1. That's even further to shorter wavelengths in the ultraviolet. So all of the transitions that go down to level 1 were hard to observe initially until we had experimental techniques and methods that could, in the laboratory, that could measure ultraviolet light. The first ones that were measured were the visible transitions, red, green, blue, that ended up in level 2. Then, as technology progressed, people started measuring transitions that ended up, for example, at level 4. or ended up at level 3. You can see these are small energy differences here corresponding to low frequency photons. Those were difficult to measure initially because those transitions correspond to energies in the infrared photons, which we can now detect in a laboratory pretty well, but your eye can't see them. All right, so here's the complete series. Now this is no longer drawn to scale, but you have the innermost orbit here is n equals 1. Look, now we're back to the original Bohr formulation. I just want you to get comfortable switching back and forth. We have the ground state put here as minus 13.6 electron volts divided by n squared. Well, n was 1, so divided by n squared, it's minus 13.6 electron volts. And then the continuum up here, as n goes to infinity, the continuum energy, according to Bohr, is going to be 13.6 electron volts above the ground, which is 0 on this scale. That's 13.6 electron volts divided by basically infinity. So that's not shown on here. It's going to be up here somewhere, right about there. As all of these 7, 8, 9, 10, 11, 12, 13, 15, 100, 500, and so on, they all blend together right about where my cross is there, where my cursor is. All right, so as you can see, again, the transitions, any transition which goes all the way down to the ground state, n equals 1, is going to be out in the ultraviolet, and there's a whole series which is going to obey a very simple mathematical formula where n1, this is the final level, is 1, so we're going to have 13.6 electron volts times 1 minus 1 over n squared. So the energies are always going to be less than 13.6 electron volts by 1 minus 1 over n squared. For example, if you go from 2 down to 1, this is going to be 1 minus a quarter. So this energy here from 2 to 1 is going to be 3/4 of the ionization energy. 3/4 of 13.6 electron volts, as you can see, is about 10.2 electron volts. That's exactly the right observed answer. How about going from level 3 down to 1? That's 1 minus 1/3 squared is 8/9. So here, the energy going from 3 to 1 is the photon has 8/9 of the ionization energy. And then this is going to be 15/16, for example, going from n equals 4 level to n equals 1 level. So those are just applications of this formula to explain the so-called Lyman series. It was measured by somebody named Lyman in the ultraviolet, as soon as he had a fancy measuring equipment in the ultraviolet. The most famous ones that were discovered earlier were by this guy named Balmer. It's not Steve Ballmer, it's spelled differently, and they had totally different personalities. But anyway, the Balmer series ends you up on level 2, and so going from 3 to 2 is a visible but rather low energy photon in the red, then there's a sort of a blue-green one, then a blue one, and then these are violet ones that you can see here coming from these higher levels. Then, as I mentioned, this next series up, these tend to be red or infrared transitions because they don't have that much energy. And then, boy, these transitions are becoming really low energy here. The ones that end you up on the 4th level, that was discovered and characterized by Mr. Brackett, the Brackett series. Everybody gets named their own series here. Pfund, I guess there's a world series probably named for the whole world here too. Just kidding. Anyway, and then, of course, these series, we stopped bothering to name them after anybody, the n equals 6 series, n equals 7 series. Eventually, these energy differences are so small that they correspond to just radio wavelength or radio frequency photons that are very small energies. All right, so that's your basic Bohr atom formula, and you should be able now, if I give you 2 energy levels, I say we're going from level 6 to level 3, level 4 to 2 or whatever, you should be able to tell me what the energy difference is just using the Bohr formula. You could write it down on your formula card, and then you can convert that into either a frequency of the photon or a wavelength of the photon, and you'll get the distinctive wavelengths that are known associated with a hydrogen atom. That's it.